Lynham. I work at Ericsson. Sorry. I lead a research team there in the networks research area, and we work on quality of experience and adapting that into the cellular network at the moment.
Thank you. Welcome. Yeah.
Okay. Morning, everyone. Yuan Yi here. I work for Disney at the Core Media Technology. So we are a software engineering team responsible for transcoding platform. Glad to be here.
Thank you and welcome. So are you ready, Enrico? Is there any logistic we should mention at this point?
Thank you. Yeah. So again, very quick reminders for especially the new people. Always be next to a Meta employee wherever you go. There is a few of us that you'll see. 11:30. I would rather make it 11:25. We have a hard stop to go to the bus tour. So the logistics are: we all go downstairs to lobby 6. We board a bus that takes us to the so-called classic campus. There, Michael will lead the way. First, we take a picture at the famous sign. Then we stop in 2-3 places, iconic places in classic. And at 1 o'clock, the tour is over. And then we have lunch at classic until 1:45. And then the bus takes us back here to resume at 2. Any questions? All clear? Okay.
Can you just check if from remote they can hear?
Just like yesterday during lunch, this is a, nobody can come in without a badge. It's a safe building. But again, if you have anything of very high value, passports, etc., please take them with you. Things that are irreplaceable. Okay.
Okay, Enrico, please.
Okay, so shall we start, right? Okay, so welcome to the JAG hybrid session this morning. We are in the first one in the morning. We have 4 presentations. Actually, mine is the first one. You can see that the title on the slide is about IGVQM, the project that we were discussing yesterday while presenting JAG Hybrid. Just a quick update about the status. There are some results to show, not that much at the moment, but I hope we are going in the right direction. So just to recap, what is IGVQM? It's Implement a Sky to Video Quality Metric. So it's a project started by Yannis a few years ago, and at a certain point during VQEG we decided to merge it with JAG Hybrid because in this way we opt to carry it out in a faster way. Let's say the main idea is still to use a large set of subjectively annotated datasets to offer some guidelines to those using video quality measures. Because if you look in the research community and also at people using this metric, sometimes it's not very clear to them how to use them correctly and so on. And everything in the project we would like to be everything in the project to be based on open data, so open data sets and reproducible experiments and so on, so that everybody can verify what we are presenting and it's not just stating as a truth, let's say. So this is the list of data sets that were identified a few years ago, and out of them we selected at the moment 5 data sets, which are the ones shown here. They include quite a variety of content in terms of really what is shown, and also the type of content, like it's natural content for the first one, gaming content for the other 2, and then also some variety in terms of resolution, coding, and so on. They are all subjectively annotated, and we have, so in short, like 100-600 PBSs out of 600 sources. I will show now some results that we currently have and that were produced actually by a master's thesis student of mine, which actually got a degree, so I need to find somebody else to work on. But anyway, it's still a work in progress. I still need to process all the results, even though we have some processing already done and also some software already published. And this is mostly to give you an idea about what we have done until now and get feedback, suggestion for you and so on. So this is about the ITS forest dataset that some of you might know very, very well, and was created by Margaret a few years ago, and includes 500 plus PBSs out of 500 plus sources. So there's quite a large variety of content inside this dataset. This is, let's say, the first graph we would like to show when we have annotated data set. So it's a graph, a scatter plot of correlation between the metrics we would like to analyze and the MOS. MOS on the, on the x-axis. And well, of course, you see the usual PSNR and VMAF, VMAF in the basic version, let's say the first version, 0.6.1. And of course, you see the better correlation, but I mean, this is sort of expected. We also try to include another metric, thanks to Yanni's suggestion, that is the ESSIM, that's actually published, made publicly available by Facebook Research. It's on GitHub, you just need to search for it. And it's quite easy and quick to compute. And you can see the results here. I mean, the Pearson linear correlation coefficient increases quite a lot from the 60.60 from PSNR to this 75 with the ESSIM. This is just for default parameters. We know that, I mean, we can change many parameters. We have some results about that, but I mean, still not ready to be published. Okay, so, and then we would like also to investigate other aspects of those this video quality methods that we are considering. So I'm just showing you a glimpse of what we are trying to do. One of the questions I mentioned also in past VQEG meetings is about the temporal aggregation strategies. You know that most of these metrics compute a value for each frame, and then you have to aggregate them to have a value for the full video sequence. And so actually, most of the metrics use a simple mean, an average of all the values, and but there are other aggregation strategies. Actually, if you go to the Netflix repository for VMAF, I mean, that's a code that can do other aggregations, and you see many other types of aggregation. I think the most interesting one at the moment is the median, which is actually the 50th percentile, which is shown here in terms of the red dot compared to the blue dots, which are the mean. Okay, I mean, there's some difference depending on how you compute these values, depending on the aggregation strategy. But I would say it's mostly limited to 1 or 2 points in terms of VMAF in most cases. And also, I must tell you that the correlation coefficient doesn't change so much. I mean, you see the values here. And this is the case in which it changes quite a lot compared to other cases just reported here. The difference is much smaller. So this is just something interesting to keep in mind. And of course, these strategies can also allow you to compute other percentiles that can be useful, I mean, in principle to draw or state some guidelines about how to use them. Another question is about implementation. That there might be different implementation of the same metrics, and like, for instance, VMAF provides, I think, 9 models on the GitHub freely available to use. Just to give you an idea of what we can do, I mean, of course, there's a floating point implementation and fixed point implementation. I mean, it's expected that they don't differ that much, but here you can actually quantify those differences, which is really small, okay? And something more interesting maybe you can do with the different VMAF versions. Okay, so this is the .1 versus the .3. I mean, sometimes there's some differences. Sometimes they are very similar. I mean, it does not depend that much on the MOS. And also, again, the correlation coefficient is still more or less the same. So, I mean, we are investigating this case just to make sure, I mean, there's not so much impact on the correlation coefficient. That is, I think, the most important metric that we need to consider when trying to use a metric to do prediction of quality, right? But I mean, we just need to be aware of the fact that using one one model or another model makes the results a little bit different, especially for some sequences. And also another thing that, thanks to Yanis again, was interesting to investigate, and we tried to investigate a little bit, is what happens when you do mistakes. I mean, very big mistakes when you use the metrics. You see the first computing VMAF in the wrong color space. VMAF was born to be computed as many other metrics on the white channel. It is the luminance channel. And we just tried this experiment. So basically, we just fed the VMAF library with an RGB video sequence instead of YUV. So basically, VMAF isolates the first channel. And if you provide an RGB, it computes the VMAF on the red. If you provide a G, B, R, and so on, it computes on the green and so on. So this is the result for this data set again, which is the one that we investigated more at the moment. And you see again the same scatter plots, and this is the VMAF computed as usual, I would say, in the correct way, okay? And the VMAF computed on the G channel, you see, I mean, there's not that much difference. You can spot some difference in terms of correlation coefficient. Actually, I would expect it more, okay, for the green one. But I mean, just out of curiosity, we did it also for the red and blue. And of course, on red and blue, which carries a much less information compared to the green for, you know, in terms of luminance, you know, it's mostly made of green. You see that the points are in quite a different position, especially some of them compared to the actual original VMAF. And again, the Poisson correlation coefficient has a difference, which is now quite significant, like 0.1 in terms of absolute scale. And again, wrong VMAF model. I mean, that's a 4K model in VMAF, for instance. What happens in case you use the 4K instead of, let's say, the full HD one? Even though, I mean, I must admit, the actual ITS4S data test is 720p sequences inside, so not really the best data set to do this test for the VMAF basic one. But you see that the difference in terms of VMAF is quite large, especially when the value is low. Like you see that, you know, I can go up to 10 or even more points in VMAF scale, which is quite significant. Even though you see that the correlation is probably not so much difference. So I mean, this is something to keep in mind. Just looking at the correlation, maybe it's not really enough sometimes to understand if things are I mean, depending on the purpose you want to use these experiments for. Maybe you should have a look at the scatter plot and maybe have some absolute references somewhere like the MOS and so on, just to make sure that I mean, you're correctly using the data for the purpose you want to. Again, I think this is more or less the last result, as there are different SSIM implementation. We know there's a paper which analyzes many of them. And actually, we have two different implementations readily available. One is in the libVMAF, and actually the other is in the eSSIM software. And so we can just compare them. And you see that, you know, at least with the implementation, these two implementations that we tested, you see that the scale, I mean, the value, the minimum value produced by, for the same PVSs produced by one implementation or the other can be quite different. Again, not so much in terms of correlation coefficient with most, but in terms of absolute value, it can be quite different. I mean, this is just you know, some results read in another way. So, I mean, we can also say like in most of the times, like 85% of the times, the difference is below 0.1, which actually for SSIM is probably quite large. Okay, but in any case, we can produce statistics like this in the context of this IGVQM project. So actually, the current status is that we have some software available. It's publicly available on the GitHub. I would say it's still requiring many refinements and refactoring because I'm not really so much satisfied of how the software is implemented. But I mean, it's working. I mean, you can test it and it's working. Probably the most important thing, I mean, from the point of view of if you want to use these data sets, is that we spent quite a lot of time to make the subjective values, transform the subjective values in a common JSON format so that it's readily available for processing using your scripts or whatever you want to use. Because basically any data set comes with its own way of presenting the data. I mean, Excel sheets and so on. Okay, so that's the next steps for this project that I envisage, and then I ask you for your feedback is, well, of course, finish the analysis and report significant results in next meetings. Include computational complexity. We're working on this at the moment, just in the form of running time, using the same computer, which is the first way, I mean, of getting an idea at least of the complexity, because some of the metrics can have quite different computational complexity. And then I would say, you know, for the presenting the data, that's just my idea, but I would like to hear from you. Maybe creating a Colab style page where you can basically have some Python code already available for, you know, doing some basic graphs, but the data is already loaded. And if you want to explore some other aspects of the data, you just type a few lines of code and you get the graphs and so on interactively. That's the best thing. And of course, we would like to start writing a first draft of this GVQM white paper or guidelines. And since I come from the academic world, of course, we would like try to publish some of the aspects that we believe they are more interesting. Okay, so let's conclude the presentation. We are having bi-weekly calls in the JAG hybrid. Basically, next one is next Monday. You are welcome to join. The time is not the best one, maybe for US West Coast, but I mean, we can change. We are flexible on these times. So I think that's all from my side. And thank you. And Yanis, you have.
Thank you. This made my day already, to be honest with you. This really personally aligns very much with the aspiration and the inspiration for that work. I personally think there is great value, even on just the things that you touched upon, because it's surprisingly not known to a whole lot of people, some of them even in the video quality community. So first of all, I want to really commend and say that this is great work. I agree with basically all the steps that you outlined. And since we do have, I see Matthias, at least his picture is there on there. So I think eventually we need to make this white paper, we can call it whatever we want to call it, easily accessible, especially, allow me to say, to the coding community, right? Because that's where we just see a small change in the implementation can make a difference. And when you're really trying to sometimes detect minor changes, extremely small changes, say in coding efficiency, it matters a lot.
Okay.
I would encourage, obviously, the computational complexity part. And in particular, and if there is interest, we can work offline, not only on the reference implementation, but optimized implementation as well, when it comes even on mobile phones. Okay. I think there is increasing demand nowadays for quality metrics to become available even on a mobile device. So it does matter a lot, right? How much, for example, the fixed point VMAF implementation. We do have our own work called CSVQM, and we can gladly add it to the mix. But this is a great place to start with. And again, I want to make sure that we are all aligned that this is, I think, a strategic vision for the group as well, to pass the knowledge we accumulate from the subjective testing, to go through the effort of unifying the formats to JSON. I think these are all great contributions.
Okay, thank you.
I have a couple of questions. One is ITS4S is mostly kind of no reference oriented database, right? Because there's you don't see actually the same content twice. So how are you computing full reference metrics. So what
Well,
am I
no,
missing?
actually, there are some sequences where I mean, there is the reference provided in the data set also for the sequences that has been shown just in the form. It's true, they are just shown in the form of the processed sequences. So yeah, that's a point we need to address. But I mean, the other data set have other ways of doing the evaluation. So yeah, that's true. Just the first idea of, well, I mean, it's more focused about the kind of results that we can get when we have the subjective value. Then yeah, just I mean, that's probably not the best data set to perform this experiment, because the most, as you said, is. I mean, maybe you should have compared to.
It might be. I was not aware that that there was.
Yeah, I mean, for the computation, we had the reference,
you
of
have
course.
The reference available.
But I mean, the point is, I mean, they were not shown to the user actually for determining the subjective value. Yeah, we cannot compute.
You don't have the demos, yeah, of course.
Yeah, we cannot compute the demos. Yes, that's a weak point.
And demos, yeah.
Okay.
No, but okay. It has other advantages. I mean, I've used ITS4S and I like it for a lot of reasons. So it's not a bad starting point at all. Yeah, the other thing was about PLCC. I mean, correlation, of course, is a simple way to compare things, especially the only fair way to handle metrics which don't provide outputs in MOSA scale, right? But still you have these problems of seeing only the correlation and not the agreement between the subjective and the objective metric, right? So you should have probably some simplest thing is an RMCE. But there's been lots of discussions on how to evaluate that. There's actually a recommendation that I think that is mostly, in ITU, I think that was mostly contributed from Margaret. So we could check about how to evaluate metrics in this overall framework. I mean, there's been a lot of discussion, and actually, I think there's an ITU recommendation on how to report. I mean, how to evaluate which metric is better than other, basically, or more similar to the subjective scores beyond just the correlation.
Okay, yeah. One thing is on the radar is do the computation of the mapping between this predicted scores and the actual MOS scores, and that could help in this regard, I think. Of course, not for VMAP, which is mostly linear, but for the others, yes. Yes, logistics or something like this. Yeah, but you're right. I mean, there's a recommendation about how to compute that, I think. Sorry. Oh, okay, Matthias. Yeah, please.
Yeah, thanks for the presentation. Unfortunately, I was only able to tune in late, but I found it super interesting. And I think there's quite some overlap with things that we are currently doing in MPEG AG5 with this CVQM dataset. So maybe we can synchronize offline also on those aspects. Probably we could maybe also make use of the code that's available there. One aspect that I would find very interesting also to add in such evaluations for the metrics, besides using something like the Pearson, would be this the ability of the metrics to do the ranking per sequence, right? Because we often have, if you want to do decision making on things and you want to decide is some tool better, a compression tool better on a certain sequence, yes or no, then you would not do the full set, but rather do look at how the let's say two variants of the coded scheme would act on this one rate point, and then it's interesting if the metric matches the MOS. So this kind of evaluation, I think, would be very, very helpful to add in the set.
Okay, thank you. That's really great suggestion. Thanks. And Balu?
Hey, is there a possibility to add some generated contents to the mix of data sets and see how some of the traditional metrics perform on generated contents? Is that being considered? That's the first part of my question. The second part is potentially like having a generic way to append the data set or the metrics in the future for something like this.
So if I understood correctly, adding generated content, right? Well,
Yeah.
actually, at the moment, we just tested, metrics which are full reference, but I mean, in principle, yeah.
Visual content, stimuli from Gen AI type style, not really natural.
Okay, but I mean, do you have a reference? Okay. Yeah, I mean, in principle, I mean, if you would have a reference, I mean, that could be already used. But I mean, without a reference, I think we need to add some no reference metrics, right, to the mix. And of course, we need the subjective scores as well. That's the most difficult part, probably. And about the second question, I'm not sure I got it. Yes, thanks. Can you please repeat the second question?
Yeah. It was more about a generic way to add other kinds of content into the data sets that you're using right now, and other metrics too, if it is possible to do that.
Yeah, I mean, in principle, we're not fixed. I mean, the software is not fixed or tied to a specific software or implementation. We just need to put some input, which is typically the uncompressed video, and run the software and get the metric, the prediction made by the software in some standardized way.
So Balu, this is Yanni. So I think the ask is simple. If someone wants to take the existing work and add a new metric, is there a straightforward way to go to the GitHub, like a handle where it says, that's how you add a new metric, that's how you call it, that's how you integrate it, or you have to reinvent it?
No, I mean,
That's to add a new metric, whether it's no reference, full reference.
Yes.
That's the point.
I mean, it should be almost straightforward, not as straightforward as I would like. So, I mean, that's why I say that the code still need to be polished and, reworked a little bit. But yeah, that's why we still have two metrics already available. And so adding new metrics and also with different parameters should be, I would say, easy, not the easiest way, not the easiest thing, but I mean, quite easy.
And the second part, the way I understand it is if I have my own database of experiments, right, with sources and PVSs,
yeah.
Is there a translation layer to put it in the compatible format? Or do I need to, again, run through the process you said to normalize and make sure it's
precisely my question? Yes. Yeah.
Yeah, I mean, regarding the subjective scores, probably you need to work a little bit. I mean, it's a JSON format, so it's quite easy to understand, and but yeah, a little bit of adaptation is probably required, I would say.
So it sounds to me, Balu, it's a great opportunity to jump in and contribute some code there to do this to, let's say, hooks, right? We need a hook that says, here is a new database, please integrate it, run some script, and the second one, here's a new metric, that's how you call it, and include it in there. And I would say the backbone of having, say, calculated in different color formats, right? We would like to have that. Because again, I've seen time and again people presenting, for example, in many modeling work, right? The loss function being SSIM on the RGB domain, right? And nobody has studied how does that, for example, correlate to subjective scores, right? How worse or even better, right? So there is this now vacuum there, a hole that people just jump in hoping for the best. So I think this will shed light in that hole.
Okay, thank you.
Enrico, one last clarification on the earlier question.
Yes.
For the generated contents, you said something about a reference. The content itself with some sort of a MOS or ground truth data should be sufficient, right? Do you need two versions of the content, one as a reference and one as a no reference?
Well, at the moment, the software has just been developed thinking in terms of full reference metrics. So At the moment, yes, but in principle, I mean, there's no reason why we should need a reference. I mean, because we just want something on which we want to compute a prediction of the quality and then relate it to the MOS. So, yeah, that's for sure an extension we would need.
Thank you.
Yeah, Dietmar, that's.
Yeah,
Yes.
thank you very much. I have a quick question. You pointed out that different implementations for the same metric lead to vastly different, or can lead to vastly different results. And I was wondering about what is the interpretation of this? If they implement the same algorithm, then, and you get a 0.1 difference in the correlation, then I would think one implementation is correct and the other one is incorrect. Or it could be the case that the algorithm is not well defined and there are some, diffuse interpretation that the implementer has taken, and one way is different from the other way. Or it could be that the method itself of the metric, the strict algorithm, is so sensitive with respect to round-off errors in the numerical computation that that would invalidate the metric. So what is your interpretation? How do you see this?
Well, at the moment, actually, we didn't see a difference in terms of correlation like 0.1. I mean, the 0.1 was just for the wrong way of using the metric. I mean, like you would like, you use the blue channel instead of the white channel, and that's for sure that's different. I mean, in other cases like the SSIM that I show, the difference is like just the 0.02, and actually it's more a difference in terms of absolute value than in terms of correlation. So I cannot really give you an answer on this. Probably they interpreted I mean, either the metric was not really well defined. Yeah, maybe Cosme that implemented one of the two can comment on this, or that there's some parameters that have been changed or they were not defined in the original paper. Not sure. Please comment.
I mean, so the reason the scaling over here is going to be different in terms of the lowest value is going to be partially to do with the pooling, right? Because SSIM uses mean pooling, there's going to be large parts of the image that have very good structural similarity, so the scores are going to be higher. In ESSIM specifically, we're trying to give more weight to areas with high dissimilarity using the Minkowski pooling, and that's why we expect the scores to be lower, because we give higher weight to the dissimilar parts of the images. But really, comparing PLCC over here on the raw SSIM scores without attempting to linearize it first with a logistic function isn't really a fair comparison of SSIM, right? Like, we know it's nonlinear. We really shouldn't be looking at it in this way, in my opinion. I think we really should go through a logistic function, fitting that, and then we can compare PLCC, or we can compare SRCC directly over here. But this is a little bit of a questionable comparison, I would say.
Okay. Just a remark, this is the SSIM, not the ESSIM.
I was about to say this. First of all, this is talking about the SSIM calculation in the SSIM library, right? There is an option to calculate SSIM. So I tend to contribute this to the differences in the filter and the pre-scaling. But the key point is, I think, what Cosmin mentioned.
Okay.
It's a highly nonlinear metric, SSIM,
yes.
Right? So actually, I can argue having a better linearity is a bad thing for SSIM, if you ask me. But at the end of the day, we need to go through a logistic function,
okay,
and then check it for sure.
Okay, thank you. Really valuable feedback. So, any other questions? So, no, I think we can move on in JAG hybrid. So, thank you. And so, I think the next one is Loic, right? Loic, are you there?
Yeah, can you hear me?
Okay, can you share the screen?
Sure, just a moment. Like it's telling me that you cannot start screen share while the other participant is sharing.
No, you need to go to the panel, Enrico.
Yeah.
Go to the panel.
Yeah.
Say stop sharing.
Ah, okay. Stop screen share.
Okay, try now, Loic.
Okay. Just about. Okay. Now you should see my screen basically.
We do.
Okay.
Yes.
Okay, let me kind of. Okay. Okay, so Okay, so let me start this presentation that is basically an informative one rather than a technical one. And it's a kind of general tool that a software that we are writing here, an effort that we are putting together in order to get a tool that will put together multiple quality recovery approaches in order to the most of everything. Okay, so let me say that I think Dietmar yesterday made a presentation that make it clear the entire literature that has been produced around in order to deal with noise in the data that we collect during subjective experiments. Okay? So it is clear that there are several approaches here, but what seems clear to most of the researchers, like I went around different conferences discussing with people, and it seems to me and many other researchers
Logic, your connection is
approaches,
unstable.
it seems clear that none of be nice. Yeah.
Can you hear me?
Yeah, I can hear you.
Okay. Yeah. Do you mind maybe turning off your camera? Because I think it really, the bandwidth is not that good.
Okay, let me.
Let's try that.
And now?
Let's go, and if there is again a disruption, I will let you know.
Okay.
Please resume from maybe the previous slide or something. Yeah.
Let me make sure that everything is rescale here. Okay. So I was here on my introductory slide. Is it better? Okay. Okay. I will continue. So I was saying basically that our general observation here is that none of these subjective quality recovery methods seems to perform well in all the conditions. Okay, and so, but we are sure that each method has its own, features and its own disadvantages. So the best idea could be that of having a single software that put them all together in order to get to get the most of all this literature. And therefore, the idea of our software here is that of having this software that will implement different methods, apply it to an input data set, and produce a PDF report that we recommend authors to publish with your data set. Okay. And we are putting some effort to get this software here, to get an Octave implementation, to make everything very free, and so that it can be used without any specific requirement. I said that none of these methods seems to perform to be nice in in all conditions and so on. But how can we? I think we can. Dietmar again or yesterday made a huge presentation to show that it is not only it is difficult to assess the accuracy of this method, but also when something works well for a specific in one case, it might fail in another case. And this simulation that I did here goes in that same sense, right? We don't have time to go into to all the details, but let me give you the idea behind the graph that you are seeing here. Basically, we want to evaluate the robustness to spammer annotators of several quality recovery approaches, okay? The quality recovery approaches are on the legends of this graph here. And we are using the root mean square error between the output of the algorithm when it is applied on a noiseless data set and the output when you add some spammer annotator to the data set. What we see, focusing on this specific application of spammer annotators, is that if you focus on the curve associated to Surreal, you see that Surreal is in general a good the best method, or okay, in many conditions, it is among the best methods. We say, okay, Surreal is very good, right? It's very robust in the presence of spammer annotator. Why RMLE, that is another method that we publish on transactional multimedia, it's basically not performing that well when it comes to the robustness, to measuring the robustness to spammer annotators. But what happens if you change a bit and you consider a different application? Like imagine you want to simulate the fact that, if the test is very long at a certain point, people get tired. And you may say there is a small probability that all the subjects, right, give a wrong opinion to a small percentage of opinion score. So how can you simulate that? By kind of changing a small percentage of the opinion score of all the subjects into a random number chosen between 1 and 5, right? When you do that, you and then verify again the robustness of, compare the robustness of Surial to that of RMLE, you realize now that RMLE is the best method, okay? But if you look at the two experiments, you see, for instance, that ESQR, that is another method that we recently published on transactional multimedia, it's doing well in both cases, okay? And you will say, okay, let us recommend ESQR at least for its robustness. But the problem is that ESQR, it's a non-parametric approach. There is no clear model. There is no, we are not in that, behind ESQR, there is not a model that explains the scoring behavior of subject. This means there is no way to use it for simulation. There is no way to do and, you know, to explain things with ESQR. Okay, you cannot explain the scoring behavior with ESQR. I hope at least that with these 3 slides, I illustrate why, you know, each method has its own advantages, and the best way to use all these methods is to have a simple software with a user-friendly interface that will allow you to analyze your data set and have a final report that will be, you know, a kind of, you know, windows on your data set. People can just read that data set and understand what is nice with your data set, what is not nice, and so on. So what about this software? It is we are completing an Octave implementation of the software. What will be the inputs? It's simply going to take an Excel file containing the raw opinion score collected during the data set. And the current version of the software is implementing the MOS and the BT500 as the baseline algorithms. Then we decided to go with a few parametric models, parametric approaches, such as Surial and Zurek, focusing on bias and inconsistency mainly, okay? Choose also a couple of non-parametric approaches. One is ESQR and NPQR. That is, NPQR is work that I'm going to present in my next presentation. And yeah, we choose the last method, RMLE, that is something that it has its own peculiarity. Like, it analyzes the scoring behavior going beyond beyond subject inconsistency and bias, trying to understand, for instance, whether people wrongly use the quality scale. Okay, like, do you favor a specific opinion score with respect to order and stuff like this? So we chose each model in order to, you know, for in such a way that the final report, PDF report that the software will produce, will be able to highlight different aspects of the dataset, okay, of the dataset that has been analyzed. And coming back to the current content of this report, that PDF, that is this report that we are going to produce. It's a file that will contain an abstract in which we'll summarize, you know, the salient point of the data set. By salient point, I mean things that look surprising or things that look current with the expectations, okay? Then there should be the usual scatter plots comparing the MOS to the output of multiple quality recovery algorithms, as well as the difference between the MOS and the output of several quality recovery algorithms. This is the basic analysis that you would like to see before using the dataset, right? Then we can move to points that are more complex, like trying to understand the application of a quality recovery algorithm to this dataset. Does it increase, for instance, the discriminatory power of the dataset? Does it reduce the confidence interval, the size of confidence interval, helping me to get a dataset that is more discriminative, and so on? So the other question of interest could be, let us look at the bias, inconsistency, and other characteristics of the subjects that participated in the VQEG experiments as a baseline or as a reference. And then ask ourselves, if we use different quality recovery algorithm to on the input data set here, get the distribution of these characteristics, is it statistically different from the distribution of characteristics from the reference data set as those from VQEG and so on, to tell the data set designer, look, your data sets in terms of participant characteristics, your data set seems to be statistically different from the VQEG settings and so on. We can do it from the subjects, we can do it from we can use an approach like ESQR that gives you a stable measure of the reliability of a single opinion score and figure out, for instance, what is the fraction of opinion score in your data set that look unreliable. Compare this fraction of opinion score with the fraction of opinion score in VQEG settings, for instance. Check whether these two proportions differ with statistical significance. This is just the points that we want to add in this report. So again, any person reading such a report in which your data set has been analyzed with several statistical methods could know, when using your data set, will know I can use the data set for this and not use it for that. Okay. As I said, we are planning to make a very friendly user interface here of the software. When we publish the dataset, it's simply going to be an Octave function called generate DB analysis report. You will feed it with your CSV file of raw opinion score, and it will produce the PDF. Okay? Obviously, there were some additional items here that I put to discuss with you. In particular, we can do more interesting things by trying, for instance, to put some more further statistical tests on this analysis, trying, for instance, to understand, is the whole data set of acceptable quality? Lucian and Jakob, I think, proposed something in this regard. I think if they are here, I would be super happy to hear about them, whether the work is mature enough to be, introduced here. And another point is, something that in the recent work from Dietmar and all, I saw they consider the possibility, for instance, to understand how participants in a subjective experiment split the quality scale. Like what does bad mean for this for people in this experiment? What does poor mean? What does fair mean, and so on? I think having this information for a given data set is important to know how you can align that data set with respect to other. So that are points that we are still considering to be included, okay, in this analysis. I mean, just to show you very quickly the current state of the of this thing here. You can, for instance, as I said, the report we are producing, it's a kind of short summary of the data set. Then you have this kind of trivial plot that you expect, right, to see how your MOS is with respect to the output of different quality recovery algorithm. Then you would like to see the histogram of differences to see whether there are a few sequences where the quality recovery algorithm, have a huge difference with respect to the baseline that is the MOS, and so on. Then you can do stuff, you can start doing stuff that are more elaborated, like trying to understand, for instance, okay, whether the distribution of qualities of the subjective quality is uniform over the scale, because this is also a fundamental point, right? And check whether if the distribution of MOS value is not uniform, can the application of a quality recovery algorithm make it, closer to a uniform distribution or something like this? Okay, so this is just it's an ongoing work. We hopefully we soon make the software available. So thank you for your attention, and looking forward for your questions.
Okay, thank you. Are there any questions? Yeah, Dietmar.
Yeah, thank you very much, Loic, for the interesting presentation. This work is very valuable for the community if the software gets published. And already just the little code snippets that you had online for the different soft outlier removal techniques was very helpful for our work that I presented yesterday for the outlier removal. So thank you very much for this. And I would like to point out to an important research question that is kind of overarching your efforts. You compiled here like 7 or 8 different methods for score or scale reconstruction. That's fine. And then we have the report. And then you see all these diagrams. Now, what would be the conclusion for someone who would have to make a choice, right? So if you publish a data set, okay, then you can also publish the report here, and the report gives you 7 different numbers of Mosses for each stimulus. And I think this is not a satisfactory outcome. We should have only one trustable Moss value here. Now, which one should we choose? And this is a difficult question. If you like to apply statistical methods like likelihood ratios and doing a p-value or calculating a p-value similar to what Lucian has done in the work for the GSD distribution, then that would work only if the outlier stuff is not in front of it. I mean, when you have the outlier stuff, as in the soft outlier removal techniques, then the statistical method doesn't work. So this is an open problem. I don't know what to do about it, but maybe you have some ideas of how to include or point to methodology that would compare these different methods and then come to a conclusion or a ranking of which one is the one that's most trustable.
Yeah, definitely. Thank you, General, for the comment. Yeah, it is indeed a point where I was hopefully I was had some hope to discuss it here, trying to decide at the end what is the quality score that we recommend to publish the data set with. But again, also for me, it's an open question, and I hope that during one of our SAM section, we'll find a way to at least discuss to find whether the solution will be, look, you have the data, decide based on your on the application for which you want to use the data set, or or at least we will go for the second alternative, trying to propose a statistical test to recommend one method over the other. But again, it's a question I hope we will have the chance to discuss within the SAM group.
This is Yanni. First of all, thank you. Highly useful. Just to Dietmar's point, I think we're going to enter a semi-religious discussion when we have to pick, let's say, what we recommend. In my opinion, it's good to have many voices. That's, I think, the pluralism is one of the big advantages. But de facto, I think we have to go at least on what is, for good or bad, standardized. So we owe it to at least offer people who are not in this field, who don't really have the patience to go through BT 500, 910, at least, hey, that's the number that comes out of, if there are multiple branches in the methodology, from branch A, branch B, branch C of BT 500, and correspondingly. That's my suggestion. At the same time, listing alternatives and arguing about what this can give you versus that is okay, but really ranking, it's something that we have to take it, first of all, internally, right? Conduct a proper, let's say, analysis and come up with yet another recommendation at that point, right? So I think our flow should be, standard is what people should be referring to when they have questions. This group does a forward research on finding what would be the next best standard. And once we convince ourselves that approach A, whatever that might be, because of reasons A, B, C, D, is really the next state of the art, push it into 910, and then add it as a standard for researchers to use, is my suggestion. Yep. At the minimum, what I would like to see coming out of a PDF like this are flags that say, hey, this observer, number 35, has quote unquote, we call it a name. We can call it outlier behavior. We can call it suspicious behavior. So at least the practitioner who conducts the subjective experiment has a guideline. Hey, what can I do to improve my data? Maybe, for example, exclude this guy. What happens if I exclude this guy, right? What are my results? Oh, now they are aligned better with my expectation. Similarly, I would like to see a similar analysis coming to stimuli, right? If we see that there are suspicious stimuli that come out of the analysis, right? Not only vertical, as I said, but horizontal analysis. That type of, let me just call it debugging information, right? It's like a guideline. Please be careful, stimulus number 32 is very dangerous. It exhibits significantly higher, I don't know, variance, whatever we're gonna call it, right? So that type of projections and flagging, without necessarily calling, okay, use this method because of this one, is, I think, very useful for practitioners, at least speaking internally.
Thank you. Yes, I think it's perfectly fit our expectation for this video because as you see, we are predicting a vertical, as you said, a vertical analysis like subject or analyze the section on subject and reliability to really, analyze subject per subject and put some flag on some subject, explaining what is happening with them, and so on. Do the same for on single opinion scores. Or as well as, we can say something on single opinion score, as I am planning also to do something on stimuli, as you said. So thank you very much.
Okay, thank you. Any other questions? Maybe not. So, Loic, you can go with the next presentation.
Okay.
Just keep in mind we are a bit late. I mean, it's not your fault. Maybe mine. But yeah, just keep it in mind, please. Thanks.
Yeah, then I will try to be very fast on this. So this is a more technical work here. It's a work that we are going to that we get accepted for IEEE 8Me in France. So, okay, and we are presenting a new non-parametric approach to recover quality in the presence of spammer annotators. And in particular, what we are doing here, we present a non-parametric way of measuring the subject unreliability or reliability, or else if you want. Use it to present this algorithm that we call NPQR, non-parametric subject quality recovery. Okay, so let me say this again, that the motivation for going for non-parametric approach is that let's say the recent literature is mainly using parametric methods, and our issue with parametric method is that you have to make some assumptions, but the gain that this assumption come with is that you have a model. Okay, so Anwi says, okay, but if we don't make assumption, then we don't lose robustness. Let us compare the two things and see at least the gain of robustness, is it valuable? So that is the gain of robustness to spammer annotator, because at the end of the day, maybe you design this approach to be robust to the noise. But again, the robustness is not everything, as Dietmar pointed out yesterday again. Let me a quick overview to the notation here. I am going to use a set S of stimuli, set I of subject, or OIS will be a random variable modeling the response of subject I to stimulus to the evaluation of the quality of stimulus S. QS will be a random variable representing the accurate the quality, okay, of the stimulus I. Now, this random variable have a distribution that we'll call PQS, because clearly what we mean here is the distribution of accurate opinion score. For the same stimulus, you have several accurate opinion scores, okay? Now, there is also the distribution of the opinion score, right? For the same stimulus, you might imagine that the subject repeat his evaluation and give a distribution of opinion score. So where does noise come from? Because the noise means basically that for a stimulus, the distribution of the opinion score of the opinion scores given by the subject is different from the distribution of accurate opinion score. That is the source of noise. When we obviously, if we could know the distribution of accurate opinion score, that is PQS, then the job is done, right? We don't know it. Normally, in the general setting of quality recovery algorithm, it's ends to find PQS, like the distribution of accurate opinion score. But this is a very difficult task. What is typically done in the literature is to get a point estimate of this, okay, a kind of small QS that could be the average of this, the expected value of this distribution here. But sometimes you are just interested in finding a point estimate that satisfies certain property, in particular robustness to spammer annotators or anything else. Okay, so we want to find a point estimate of this distribution here. Now, to do that, what we do is we introduce a statistical measure of reliability, okay, of a subject. And to that end, we consider two aspects. Okay, we say we want to consider the so-called interstimulus consistency. What is the interstimulus consistency? Is the ability of the subject to rank the quality of two stimuli. If I give a subject stimuli A and stimulus A and stimulus B, I expect the subject to say A is better than B when objectively the quality of A is better than the quality of B. So how can we measure the interstimulus consistency of a subject? Maybe by using a very empirically well-known measure as the Spearman rank order correlation. We can take the mode of the opinion score of the subjects for all the stimulus, take the mode of the opinion score of the accurate, take the mode of the accurate opinion score, and then, or the simply the mode of the, let's say for each stimulus, we take the opinion score chosen by the majority of the subject and correlate it with the opinion score given by the subject to get an idea of how the subject is consistent in terms of interstimulus evaluation, okay? But this for each subject I, we define this, we call this correlation CI, but obviously if we expect this CI to be positive. But if this is not the case, this probably means that the subject misunderstood the task. He's so-called an inverted rater. For us, we decided not to keep this kind of subject into the loop and truncated the correlation. So our definition, our final definition of interstimulus consistency is the maximum between 0 and the correlation between the votes of the subject and the votes chosen by the majority of the subject. So this is the way we compute the interstimulus consistency of the subject. No, the reliability according to us, the reliability is not limited to that interstimulus. We need to consider a second aspect that we call intrastimulus consistency, okay? And in this case, given a stimulus for which we know that the distribution of accorded opinion score is PQS, and the subject the subject I is rating according to POIS, we can measure the inconsistency of the subject with the distance between taking any measure D of distance, of divergence or distance between the distribution that the subject is using and the distribution of accurate opinion score, right? So what you can do is you can give the following definition of intrastimulus consistency. You can basically sum the distance between, sum the distance between the distribution used by the subject and the distribution of the accurate opinion score. Take the average of this will give you the average and consistency, but we need the consistency. So you inverse everything and you get TI, that is basically the average intrastimulus consistency of the subject. The problem with this formula is that POIS is the distribution of the opinion score of subject I for stimulus S. This means to get even a trivial estimate of this distribution here, you need to get several evaluation of the same stimulus. This is very difficult in practice. It is already very expensive to get one observation for each stimulus. So what we did is that we need to call the theory in half here, right? And what happened is that if you choose this distance D, because so far D is just a free pair, you can use any distance between two probability distribution. If you choose this distance D in a way that it is an expected value, that you can expect it as an expected value of a function of the distribution of accurate opinion score and the observed opinion score, if the variance of this random variable inside the expected value is limited, then what you can do is that as the number of stimulus rated by the subject tends to infinity, the intrastimulus consistency can be expressed as you see here, as just a function of the observed opinion score and the distribution of the accurate opinion score, right? You see that the distribution of the opinion score of the subject for one stimulus disappear. So we can use this formula even though we have one opinion score for each subject for each stimulus. Okay. Obviously, you still wonder what is this function? How can we get this function f then? To get this function f, you need to ask yourself again how you want the you want the intrastimulus consistency to consider two aspects: the ability of the subject to repeat itself. Okay, for the same stimulus, you should repeat yourself. You can measure this with the entropy of the distribution of the opinion score that the subject is given for each stimulus. And then you want the subject to be accurate, okay, to repeat, to be accurate. So the distribution he's using should not be that far from the distribution of the true opinion score. We can use the KL divergence. If you sum the two aspects that that contribute to the intra-stimulus consistency, and use the property of the logarithm, you can express the distance as an expected value, as we are saying. And the function that you see inside the expected value is the logarithm. So our x function, we get this definition of the f function. And now you can insert this f function here into a formula to get the overall reliability of the subject. And we express it as the multiplication of the inter-stimulus consistency given by this max between 0 and the correlation, and the component coming from the intra-stimulus, okay? And this is our measure of reliability, okay? The overall reliability of the subject. And obviously it's a non-parametric measure of consistency, okay? To compute it, you need an estimate of this distribution PQS, right? That again, by definition, it is the distribution of accurate opinion score. Okay, we don't know. If we knew it, then the problem is done. There is no way, there's no point of doing all the analysis, right? But in fact, we do all this analysis because it is super hard to get PQS. So, but what we can do is to take a very rough estimate of PQS, use it to compute the reliability, and hopefully use that reliability to define a point estimate of the quality that has the property that we expect. And in fact, for our estimate to implement our NPQ algorithm, what we did is to take the simple possible estimate of this PQS by just taking the empirical distribution of the opinions, okay, for the stimulus S. We insert it, we use it for our algorithm, calculate our rough estimate of the reliability of each subject, and weight the opinion score of each subject with this reliability to get our estimate of the quality of each stimulus. Now, experimental setup, we kind of use run experiments on data set collected in lab, as well as 3 data set collected in crowdsourcing setting. In the lab experiments, the quality, we assume that the quality of the data is good enough, and that in order to add spammer, we need to simulate them. In the crowdsourcing experiment instead, what we did is that we cannot, the quality of the data is obviously corrupted. So what we call spammer are the subjects that all the many methods agree that they are unreliable, okay? And I will give more detail later, but we did the experiment on controls and crowdsourcing experiment. Again, when it comes to controlled environments, we add the spammers ourselves and use the root mean square error between the output of the algorithm on the noiseless data set and the output of the algorithm after adding the spammer annotator. Again, the lower is the root mean square error, the most robust is the approach. As you can see, for all the 4 data sets, again, MPQR, that is our proposal, is at the lowest root mean square error. It is interesting to see that when it comes to as an ablation study, we tested, you know, we use only the intrastimulus or only the interstimulus consistency as measure of reliability, and in every case we get lower performance, meaning that both components contribute to the algorithm performance. As I said before, it's super hard to know to define what is a spammer in a crowdsourcing experiment, right? Now, if we take approaches like MPQR that we define, MPQR has a clear definition of the reliability of a subject. If you take Surreal, that is written here as ITUP 913, but okay, it's a detail. If you take Surreal or Zurek, they have the inconsistency of the subject. That is the measure of unreliability of the subject. So these 3 approaches here have the way you can use these 3 approaches here to rank subject based on their reliability. So we computed the 3 approaches for all the subjects on each data set, rank the subject based on their unreliability, select the top 5% unreliable subject for each approach, and then find the subjects that belong to the intersection of these 3 sets here. So find the subject that the 3 methods agree that they are spammer, they are highly spammer. We then exclude this subject from the dataset, then compute, use the method on the dataset without these these common spammers, and then progressively add the spammer to the dataset. And every time we're adding a number of spammer, we were reapplying the method to see how the root mean square error is changing. And again, in this experiment, we saw that NPQR, it's, again, much more robust to the addition of spammer annotator coming from from these common spammer annotators. Okay. So the point here, what we can see here is that, okay, NPQR seems to offer higher robustness, probably due to the fact that it's a non-parametric approach. And also when it comes to the reliability, the experiment showed that it is important to consider both the interstimulus and intrastimulus consistency. That will be all. Thank you.
Thank you. Thank you. Any questions? Yeah.
Hi, Loic.
Yeah, hi.
Hi, this is.
Yeah, you're on.
Okay, this is Pablo.
Hi, Pablo.
Hi, good to speak with you. I saw the presentation that you are using the empirical distribution to estimate the overall, ground truth distribution of scores.
Mhm.
There's a paper. There's a paper from Jakub Nawala a couple of years ago where he was, kind of contributed a bit to the paper, but that's not the thing. He was comparing different distributions, the properties of using different distributions as basically to bootstrap results, so kind of as ground truth.
Mhm.
And both well-developed underlying normal distribution or the generalized score distribution, both of them offered better results than directly using the empirical distribution. So maybe you could check that, and
Yeah.
it might help.
Okay, then Pablo, this opened the door to a so-called an hybrid approach, because what we didn't want to do is to use a parametric estimation of the distribution. Okay, to not to change the nature of the method. As long as the estimation of the distribution is non-parametric, that will be not expensive computation. That will be super. We'll be super happy to do that. Otherwise, we will need to redefine the research direction here, trying to test how good a hybrid method, like taking a non-parametric component at the last moment, like, including just the notion of parametric statistic, just for this for a better estimation of the distribution of acquired opinion score.
Okay, yeah, I see your point. Okay. On the other side, Han, maybe you could simply check if results are much different, and it will kind of show how,
Definitely.
an idea of if this research direction that you're taking kind of makes sense. It's a too strong thing, but okay, how it compares with other approaches.
Okay, definitely. Thank you.
Okay, thank you. Any other questions? Cosmin? Okay. Okay, thank you. So let's go with the last presentation, right? Yeah. Okay, so Maria, are you online, right?
Yes, I'm online, but I cannot share yet. Let me try again.
Hi.
Yes, it works.
Yeah, it works, Maria. Go ahead.
Okay, let me just, I wanted to also maybe activate the camera if it works, but okay, I think I will go ahead without the camera. Okay, so hello everyone. So for those who do not know me, I'm Maria Martini. I'm a professor of multimedia communications at Kingston University, London. And what I'm going to present today is not a fancy presentation of immersive systems as we do sometimes, but a presentation which is very much based on mathematics and statistics, the classical way. So as the theme was mentioned before, and this will also address SSIM, and in particular the transcoding quality based on SSIM for DCT-based compressed images and video, and also similar types of images and videos which meet the same requirements that I will mention later on. So we can see here a scheme for transcoding, a block diagram for transcoding, where we can see the original video, the first encoding, and then the transcoder. And we can see the qualities that I have highlighted here. So as Q1 is the quality after the first encoding, Q2 the quality after transcoding with respect to the video input to the transcoder, and Q tot is the total quality. So the quality of the transcoded video versus the original video. What is done very often is that what is calculated is actually what is highlighted as Q2 here. So the quality of the transcoded video versus the video at the input of the transcoder, but not the original one. The problem is that the video at the input of the transcoder in some cases do not have a good quality itself because it comes from another encoding or it was captured in not ideal conditions. So the actual quality of the video after transcoding is what is Q tot here. So what I'm addressing here is what is the relationship between these three qualities, Q1, Q2, and Q tot, in particular in the case of SSIM. It may seem intuitive, but what I notice in the literature is that first of all, there are not many works trying to address these, and in one or two cases where they need this relationship, in one case they consider the mean of the SSIM as the global quality. In one case, they didn't mention additivity explicitly, but they calculated Q2 as Q tot minus Q1 in terms of SSIM. But as we will see later, neither of these is correct. So maybe you can think at what you would think is the actual relationship between the three. But I can go ahead with the presentation. So the first part is based on the presentation that I did in Klagenfurt, since the assumptions are the same. So I assume here that for DCT compressed images and video, the mean of the error is 0, and the mean of the image or frame before compression is the same as the one after compression, and the same is valid for the variance. We can see here an example for JPEG, and what I did here is to compress, I don't know if you can see my cursor here. So what I did was to compress a JPEG image from top quality to low quality. Here is quality factor 10 is the lowest quality, and calculate the mean. So you can see that here it appears oscillating, but if you check the scale in the vertical axis, this is very much zoomed in, and this would be seen in a scale from 0 to this value as a horizontal line. So the mean has a very small variation with compression. With variance, the variation is a bit higher, but still not high. And if we consider quality values above a certain value, which are the values of interest, for instance, for video streaming, when we do transcoding for video streaming, we want the quality to be above a certain value. We can also assume the variance constant with compression, so as the compression factor increases. This was a global scale. If you want to check the local scale, here I provided some plots for the block variance, so the same case. So this was for the baboon image. For the first 5 blocks, I calculated the variance, compressing more and more the image. So you can see, for instance, in blue here, this is the first block, and the variance has some variations, but not major. This is the second block, the third one, fourth block, and fifth block. So again, even if there are some oscillations, assuming this is constant does not result in a major error here. Now let's go to the derivation and a reminder of the expression of the SSIM. So we can see that in SSIM, we have the mean of the original and the compressed image or frame in a video, which results in different parts here. The variance of the original and the compressed image, and the covariance, which is a particularly naughty term, a term that we don't like, because to calculate the covariance, we need to compare directly the original and the compressed version. So I will split the derivation in two parts here, the derivation of the relationship that I mentioned between the different qualities. So the first part is the relationship between SSIM and mean square error. For those of you who attended the Klagenfurt meeting, I presented this part already, but I will go through these briefly and then move to the second part, which is the new one. Again, given this expression for the SSIM that you can see here, with the assumptions that we did on equal mean before and after compression and equal variance before and after compression, this expression results in this one. And in this one, you can see that there are two terms which are identical, this one and this one. So we can remove them. So with the assumption of equal mean and equal variance, this is the expression we have for the SSIM. Then we can do some considerations to get rid of the covariance. And we can consider the error as a random variable, and the variance of the difference of two random variables, x and y here, has this expression that I've reported here. So if we isolate this term becomes equal to this one. If you replace it here, this is what we have for the SSIM. So just doing the division, we have 1, because this term and this one plus this one is equal to this one minus this value here. We can observe that with the assumptions we did, the mean of the error is 0, as I mentioned earlier. So this variance, the variance of the error, is the mean square error. So this expression is equivalent to this one. And if we do the mean, since the SSIM is typically calculated over blocks or windows, so sometimes Gaussian windows, sometimes rectangular blocks, something was mentioned before about different implementations of SSIM. So if we calculate it in blocks and then do the mean over the image, this is what we have. And we can call it as MSSIM here to distinguish from this one. And this is the mean of this one here. Now let's move to the second part of the derivation, which is the new one. I promise this is the last slides with a lot of mathematics. Okay, so the part 2. So let's consider the error that we have with the encoder 1, and let's call it E1 here. The error we have the encoder 2, and we can call it E2 here, and the total error that we can call E. For the assumptions that we did, we can say that all are approximately 0. So the encoding error of a DCT-based video codec has approximately 0 mean. So we simplify this because these are all zeros. So if you consider this for the calculation of the variance here, since these are 0, these are the expressions of the variance that we have seen are equivalent to the mean square error. So this one is the mean square error for the first encoder. This is the mean square error for the second encoder, so for the transcoder. And this is the total mean square error, so the actual quality of the transcoded video versus the original one. Now we can write the variance of the total error this way. Again, this is the variance of the sum of two random variables, which has this expression, where this term is the covariance. Now we have to do another assumption that I will show later is probably the strongest one. So I have to assume here that the two errors, E1 and E2, so the errors associated to the two encoders, are independent. So if I do this assumption of independency, I can write this expression here this way. And this is equivalent for what we have seen before. This is equivalent to say that the mean square errors are additive. So the total mean square error is the mean square error of the first encoder plus the mean square error of the second encoder. But what happens in terms of SSIM? This is what we are interested in. So to check the relationship in terms of SSIM, we can consider the approximations that I provided for the SSIM for the first encoder and for the second encoder. So we can say that SSIM1 for the first encoder can be written this way, and the one for the second encoder can be written this way. And for the total can be written 1 minus mean square error total divided by this value. Mean square error total we have seen is the sum of these two. So the total SSIM can be written as this one. We can split these in two parts as here. So this we become 1 minus MEC1 divided this minus MEC2 divided by this. And then if we just add 1 and remove 1 here, add 1 and subtract 1 here, we can see that we have SSIM1 here. Adding the 1 here, we have SSIM2, and then we have the minus 1 that we had to subtract. So the total SSIM can be written by the sum of SSIM for the first encoder, the SSIM for the second encoder, so the transcoder, minus 1. And here is the final relationship then that we have identified. So this is for the definition I've given before. If we consider these at a local scale, this is also true at the global scale, because we just need to sum over the blocks each of these terms. So what we have is the total M mean SSIM over the image or the frame is given by the sum of the two minus 1. So we can see that what considered in some works actually was not correct, following mathematics, statistics, and these assumptions. We can do some considerations here. First of all, SSIM1 here, or MSSIM1 here, in some cases is not easy to calculate. In some cases, for instance, the video is ingested in a system from users, and we don't know how it was encoded and what was the original quality. It is possible in this case either to extract it from metadata or to estimate. There are some methods to estimate the SSIM with no reference. Or even reduced reference by considering, for instance, information in the bit stream. But this is in general the relationship. So the sum of the two minus 1. An example here in terms of results. I considered again the same image that I consider here as an example throughout this work. So the baboon image, which is often used for signal processing and quality assessment tests. And I encoded this image first with JPEG at quality factor 70, and then transcoded with different quality factors from 50 to 100. And the results are reported here. So these black curves with stars, so with asterisks, is the total SSIM. So the SSIM calculated after transcoding with respect to the original image. This one, the purple one, is the one estimated with the expression I provided. And the blue one is the value calculated for after encoding with quality factor 70, so SSIM1. And this is SSIM2, so the quality we have for the transcoded video versus the video which is provided as input, the image in this case. So the image, the JPEG image at quality factor 70. So we can see that the two curves are quite overlapped. So the estimation follows quite well what we can consider the ground truth, so the black one. I remind here that there were two main assumptions. So the mean of the encoding error in the first encoder and transcoder is 0. We also had the assumption for the variance, of course, but also that the coding errors produced by the two encoders are independent. And in my view, this can have an impact here. This is an assumption that has been used in other works. And this is a valid assumptions, but not perfect. So this could be probably the main cause of these slight differences, because the mean I've seen in other cases that is a very strong assumption, very valid assumption that does not result in discrepancies typically in the performance. Okay, so yes, these are the conclusions. So the accuracy is high for this approximation. The relationship is very simple, so this can be used for analytical optimization problems, SSIM based. And the assumption is good for a good quality range, which is of typical interest. So when the quality is, I would say, good enough as when used for the case of video streaming. If you are interested in further information about it, you can check the associated paper here. So the first part of this paper is what I have presented already in a previous meeting. And the second part, what I presented here is the second part that provided this as an example of utilization for this formula, this expression.
Okay.
Okay.
Thank you.
Thank
Thank you, Maria. Any questions?
Maria,
Quick
this is
question.
Yanni. Thank you
Hi,
very
Yanni.
much. We really don't do justice to your work because you are squeezed by time. So I would like to maybe schedule, I think for me, the key takeaway that I have been shouting for many, many years, we should not be adding quality or averaging, we should be adding distortions. That's really what's behind the framework, and that's why I really like it. And the assumptions you made, I think, are more reasonable. But again, I think a good discussion can either be done offline or maybe in a follow-up, because I think there is a lot of meat in this presentation that now, because we're under pressure, I don't really want to squeeze it. But I'm personally very, very happy with the work. Thank you for presenting.
Thank you. Yes, let me know if you wish to discuss it later at some point. Happy to do it.
Yeah, we'll see and if we can put in the schedule. But we really have to, again, maybe do a break now, so we are on time for our tour that's following up after the next presentations. Thank you again, Maria.
Thank you. Thanks, Yannis.
Stay
Thank you.
tuned for maybe adding a slicer.
Thank you.
So let's stop the recording. I need your help to please come back in 10 minutes.